Heat waves, drought, tornadoes, hurricanes, floods, blizzards, bitter cold. Extreme weather has an incredible impact on people across the globe. On Mount Washington, our scientists brave some of the worst weather on the planet to improve our understanding of our warming world.
And hello, everyone. I'd like to thank you, teachers and students alike, for joining this week's virtual classroom. My name, of course, is Francis Roswitz, and I'm a weather observer here on Mount Washington, as well as an education specialist. So the way we're still doing things here is pre-recording these episodes, and then about a week later doing a question and answer session that's live with either myself or Alex. And so be on the lookout for those opportunities every Tuesday at 11:15 a.m. So I want to get into today's topic, which is weather forecasting and sort of the how, the why, and some of the challenges associated with it up here on the summit of Mount Washington. First of all, just how do we predict the weather? Well, we use a combination of tools in meteorology. We use satellite, which is an orbiting satellite well above the planet that's taking samples of our clouds and temperatures. We're also looking at radar, which are towers that send out high energy beams of radiation to clouds and detecting the rainfall within them. Excuse me. We're also looking at weather observations and numerical models, which weather observations actually really do help these numerical models help to paint the weather picture. And I'm going to talk about what exactly a numerical model is going forward. But first, we'll start with weather, or rather radar and satellite. And so you're looking here at a classic image of a satellite over the Northeast. And so these white areas you're seeing are clouds. And I want to point out some individual features here that we'll notice. Get my pen out. There we are. You'll notice that a few of these clouds have different shapes. Some of them look a little bit more textured, like the ones over parts of Canada and Maine. And while others look a little bit flatter, like the ones over New Hampshire and portions of western Maine, I should say. And we'll see how that correlates with the radar image. This actually relates to the precipitation intensity. So those puffier clouds are going to produce heavier rainfall, which we can actually see over portions of western Maine or eastern Maine. My apologies. And then lighter rainfall, of course, occurring over New Hampshire with those flatter clouds, those stratus clouds. And so the observations of cloud types can be done from space as well as up here on the summit as well. Oops. So we'll get out of that. We'll move along to weather observations. We'll go to the full screen for this one. This is looking at a map of observations around New England. You don't have to be too concerned about the symbols, but generally what you're seeing, those little lines are areas, or rather measures of wind speed. And then you can see a bunch of different numbers. Those correlate to temperature, pressure, and a lot of the variables that we discussed in the last program. And so I'm going to transition now to what exactly a numerical model is. This is a mathematical representation of the atmosphere, and it's based on those weather conditions. So those start off are the equations. And so in each of these grid boxes you see behind me, we break the planet apart in small grids, and we do equations in each one of these grids. So it adds up to a very large number of equations, hundreds of millions, even billions of equations. So those observations get the model started. And so in this slide, I want to point out there are 200 million, or 210 million, I should say, weather observations taking place every day, just in the United States alone. These observations are then getting entered into a vast array of computer models. And then these forecasts from the computer models get displayed in a way that makes sense to us meteorologists. So here we're seeing areas of green showing rainfall and areas of blue showing snow. Then those tight isobars, those tight lines you see showing potential for wind and pressure. And so meteorologists make sense of the models to make sure that they're actually physically making sense if this type of weather is actually possible. And so while their computer models are great, there's still the human element. Are all the models the same? Well, there's actually hundreds of models. In America, there is the GFS model as well as the NAM model, and these stand for Global Forecast System as well as the North American Mesoscale model. The GFS has a longer range, and it's a little bit less fine in its details, where the NAM has a shorter range, but can actually resolve things like individual thunderstorms. And so here's an example of a model disagreement. This is the track, the forecaster track, I should say, of Hurricane Sandy back in 2012. Each one of these little lines you see is a potential track from a different model. So as a meteorologist, you look at this and you have to make sense of models all the time. So up here on the summit, our observations do contribute to these models. Actually, weather observations are, again, as I said, are the starting point for the models. They get them spun up. They're the initial conditions, we call them. And the more accurate the observations are, the more accurate the weather models are going to be. And Mount Washington is unique because we act like a sort of a stationary weather balloon. We are up here in about the mid-troposphere. We can sample weather 365 and 24/7, whereas the National Weather Service can only launch 2 balloons a day to sample the atmosphere where we are. That's still quite good, and we are able to forecast the weather to a pretty good degree of accuracy, but still having that 24/7 access to the middle troposphere is actually really, really awesome. So forecasting up here on the summit, we do a 48-hour higher summits forecast. That's twice a day, and the variables we're looking at and forecasting for our hikers and recreators include temperature, wind chill, wind speed, and gusts, as well as sky conditions, and finally precipitation. So this is an example of one such forecast. And so, oops, my apologies. So just why do we forecast at Mount Washington? Well, we've got a lot of different people sharing this space with us, especially during the summer and spring months, as well as the fall. We've got thousands of people traversing up the auto road. We've got probably hundreds of thousands of hikers and people doing recreation and travel up here. So we want to make sure that they're safe with Mount Washington's extreme weather. But it does not come without its challenges, and I have certainly gotten a couple of forecasts wrong in my time up here so far. So mountains, they tend to make or break weather, we say. And so through a process known as upslope, precipitation can actually vary quite rapidly just on the same summit here on Mount Washington. What I mean is winds approach a mountain and then they get forced up and over. That mountain's not moving anywhere, of course. And so they rise, they condense into clouds of precipitation. So the windward side here, the wind-facing side, tends to get a lot more precipitation than the leeward side, where the air is actually coming down the other side of the mountain. It's warming and drying out. And so the weather here, a little bit better, but also drier. And so in a lot of mountainous climates, this is a huge area of forecast uncertainty and a big forecast headache up here on the summit as well. We have other challenges up here on the summit. I mentioned that weather radar and how it's sending out those beams of radiation. Well, we have a weather radar based out of Maine, and that's sending signals in a sort of a cone-like shape. And so the issues with that include the beam actually getting blocked in the middle of the mountain. So it only hits us at about 4,000 feet. It's not seeing what's going on the summit. And so our rain and snow observations are really important up here. We also have to deal with enhanced winds. While winds in the valleys may be 10, 20 miles an hour, winds up here could be north of 100 miles an hour, and our equipment could actually be damaged from those winds. And speaking of damage, what I'd like to bring to your attention here is a nice picture of Rime ice. While it looks beautiful, it does damage our instruments from time to time, so we do have to de-ice them. And of course, it could affect the data that's going into those weather models that I talked about a couple of slides ago. So sort of bringing it all together, some of the main ideas from our presentation today. Forecasting does require a lot of tools, and the most important tool is the forecaster themselves. They have to look at all these different variables and sort of make sense of what's going on. There's many different models to choose from, enough to make your head spin at times as a forecaster. But you have to know that each model is a different level of accuracy. They all have their strengths and weaknesses. Models have different time scales, so they go out in different lengths of time. For example, the GFS goes out to 384 hours, while that NAM model I discussed only goes out to about 84 hours. So very large difference in time. Observations are key. And observations, of course, are the starting point for those computer models. And the better the observations, the better the forecast, as we know now. And then finally, forecasting for a mountain is just plain hard. And so speaking of forecasts, I'd like to touch on our forecasting capabilities up here on the summit. And so I will be right back. I'm going to pull up our forecasting website. We found at mountwashington.org/forecast. There we are. All right, hello everyone. This is our higher summits forecast, and how these are broken down. We do our forecast summary. So just pull it on full screen here. That first part is discussing sort of the players on the field, the cold fronts, the high pressure systems, the low pressure systems, everything that's contributing to our weather on a given day. And then we go down and we look at the daily variables. And so we're looking at, again, our temperatures, our wind speed and direction, as well as wind chill when we do have those wind chill values that cause, dangerous conditions like hypothermia up here on the summit. And so again, these go at 48 hours. It can be found anytime at MountWashington.org. We've got our night observer who issues one at 4 a.m. and then, of course, evening shift issues the one at 4 p.m. I also do want to mention, as we wrap up our presentation here, more virtual classroom resources. You can, of course, find pre-recorded virtual classrooms. If you missed last week's, for example, you can find it at mountwashington.org/classroom. You can also find links to our live Q&A with each of these lessons. We've already got a few of our lessons posted up here on the website. And so, of course, check these out if need be. Going back to our presentation, here's just some of our contact information. And of course, information that has to do with registering for our question and answer. That can be found at mountwashington.org again/classroom. And you can also submit questions to me for the virtual or the live Q&A, I should say. My email is ftarasowitz@mountwashington.org, or you can send it to our education account at education@mountwashington.org. I'd like to thank everyone for joining, and I hope you have a great day. All right, I'm all set.